Dear friends, today I will explain to you what we mean by DC resistance of the diode, AC resistance of the diode, what the difference between the two. So this is our PN junction diode, P and N. Okay, this is, P, this is N. Now, when it is made forward biased by connecting P with positive and N with negative, so the current starts flowing, the diode current, P to N, positive to negative. Okay. When P is connected with positive, N is connected with negative, then PN junction is called forward biased. So when it is forward biased, we draw a graph between the biasing, mean the voltage which is given to PN junction. Let we are giving a variable voltage to PN, forward bias. Okay, we're going increasing the forward bias 0, 0.1, 0.2, 0.5 and so on. And we find that what is the current. So we measure the current with the help of milliammeter. That is called the diode current. Then we draw the graph. It is of this shape. Now the problem is, what is the resistance of the diode? One thing is very clear. As it is a curve, the graph is a curve, not a straight line. If you have a straight line graph between V and I, like this, then the resistance is constant. But if we are having this type of curve, so its slope is increasing continuously, then here the resistance is not a constant at every point. The resistance will be different at the different points. So exactly the same here. So it is a curve. Okay, so the resistance will be different at the different points. And the resistance depends what is the voltage which is given to the PN junction. If the voltage is given like 0.8 volt, what is the resistance? If the voltage is 0.5, then what is the resistance? Because when the diode is used in practical application, then a fixed voltage is given to the PN junction. Then it is having some resistance because of the fixed voltage. So let's say the fixed voltage is 0.5. Okay, 0.5, just before the knee point. You know what is the knee point? Before knee point, the current is very small, and after the knee point, current rises sharply. Before the knee point, the current is small, but after the knee point, there is sharp rise in current. Okay. So just before the knee point, the voltage is 0.5. And at this voltage, you just note down what is current. Current is here 2 milliampere. So if the current is 2 milliampere, what is the resistance? And this is called the DC resistance, because we are talking for a fixed voltage. At a fixed voltage, what is volt, what is potential, and what is current? Potential is how much? 0.5 volt. Current is how much? 2 milliampere. Just note down, it is 2 milliampere. Now millimeter 10 raised to power minus 3. Just solving, and it comes out 250 ohm. So at this point, if this voltage is given to PN junction, then PN junction offers 250 ohm resistance. But if this point is chosen and correspond to this point, what is the voltage? 0.8. Now we find resistance for this particular point. Here the voltage is 0.8. And what is the current flowing? Okay, current flowing is 20 milliampere. Now just dividing the two, and we got 40 ohm. Notice that at this point resistance is quite small, because the current, there is a sharp rise in current, and moreover from here to here the graph is approximately a straight line. That means resistance at this point will be approximately near about 40 ohm. It will be same, because it is almost a straight line. Now the next problem is, what is the resistance at this point? This is reverse biasing. P is given negative potential and N is given positive potential. Okay, for reverse biasing you find the diode resistance. So diode resistance becomes, what is voltage? 10 volt. And how much is the current? Very, very small, 1 microampere. Now dividing the two, how much it becomes? 10 meg ohm. So this is 10 meg ohm. Where? For this point. So reverse biasing PN junction behaves a very, very high resistor. It act like very high resistor. But when it is forward biased, its resistance depends upon the voltage or upon the where is the point you have chosen. Okay, so resistance at this point is 250 ohm, this point 40 ohm, this point 10 meg ohm. So this is all about DC resistance, mean for the fixed voltage. Now we coming, if sinusoidal, PN junction is given first of all some fixed voltage, and that voltage maybe corresponds to this point. Then a signal is applied to PN junction, and signal is varying like this, is going to positive and negative. When signal is varying, what happens? When signal is going to positive, the applied voltage becomes more positive, right? And when signal goes to negative, signal goes along the negative direction, the applied voltage decreases. If the signal is applied to this PN junction, then whatever the voltage given before the signal, that voltage varies according to the signal. It becomes positive and negative. The voltage then, the resultant voltage swings about this point. And when the voltage swings about this point, the resistance of the PN junction also swings. That swinging resistance is called AC resistance, and we have to find that. Okay, it's understood, I think. So let's say about we are interested, like this was our operating point, and we have applied a voltage, how much? we have applied a voltage approximately 0.7 to the PN junction, right? Then the current was flowing 2 milliampere. When this signal comes, then this 0.7 voltage swings between this to this, between this value and this value. Mean the swing is 0.76 towards positive side. Mean when positive of the signal comes, then it swings towards positive side, becomes 0.76. When negative half comes, negative cycle comes, it becomes 0.65. Okay, then what is this total span? It is this minus this, that becomes 0.11 volt. Then we find what is the swing in current. Okay, when positive comes, the current becomes 4 milliampere. When negative comes, the current becomes almost 0. So 4 milliampere minus 0 milliampere becomes 4 milliampere. Now we find the diode resistance. Diode resistance means delta VD, change in the diode voltage and change in the diode current. That is what this 0.11 volt divided by 4 milliampere. So 0.11 volt divided by 4 milli, not 0.11. So delta VD is 0.11 volt divided by 4 milliampere. And result becomes 27.5 ohm. So here the resistance is AC resistance, mean varying resistance. When the signal arrives, then the resistance, the shift in resistance, that is 27.5 ohm. That shift is 27.5 ohm. That is called the AC resistance. About this point. Now we are interested, what is the shift corresponds to this point? Okay. So what is change in current? If this signal arrives, the current increases 25 to 30. Negative comes, it becomes 25 to 20. The swing is, this is the swing, 30 to 20. Mean delta ID is how much? 10 milliampere. Now what is the change in voltage? Very, very small, because here the current is, there is sharp rise in current. For small change in voltage, there is a large change in current. So what is change in voltage here? So the voltage change is very small, 0.8 when positive comes, 0.78 when negative comes. So this change is only 0.2 volt. Then what is the resistance? It is 0.02 volt divided by what? 10 milliampere, and it comes out only 2 ohm. So here resistance is very, very small, only 2 ohm. If you chosen this point, well, this resistance, this resistance means variation. When this signal comes, the resistance varies. How much? The variation is of 2 ohm, because this line is almost linear, and the variation in resistance will be very small. Okay, so this is the variation in resistance. This is called AC resistance about this point. Now on the other hand, if we find the static resistance, okay, if we find the static resistance corresponds to this current is 25 milliampere and correspond to this voltage is how much? 0.79 volt. Static resistance becomes RDC 31.62. So this is the DC resistance at static resistance at this point. What was the AC resistance? That was the variation when the signal comes, and that variation is what. Similarly, you can find what the resistance at here, the DC resistance. What is the voltage at here? 0.7. What is the current at here? This current is 2 milliampere. So what is the DC resistance? This is 350 ohm. So this DC resistance is different. AC resistance is just the variation. Now we are going to establish a relation using a formula. Just see. Resistance from the formula. AC resistance we are going to find. This is the diode equation. You are quite familiar for this equation. Very simple. This is the reverse saturation current. K is some constant. Okay. VD is the diode voltage which is applied to the diode. Tk means temperature at the Kelvin scale. -1. E means exponential. Now just open the bracket. Differentiating it with respect to dID over dVD means differentiating this equation with respect to the diode voltage. Is is constant. So this is the differentiation of e raised to power, the factor. Mean differentiation of this and differentiation of Is. Because Is is the reverse saturation current, it is a constant quantity for a diode, so the differentiation becomes 0. So only the differentiation of this factor. So dID over dVD becomes Is this. So first of all, exponential factor as it is, then the differentiation of the differentiation of just the power of this, mean this one. So here constant is here. K over Tk is constant taken here, and the differentiation is only of Vd. And that becomes 1. This is ID. So dID over dVD is KID over Tk, and then now this is ID. Okay, this factor is 1. Now what is K? K is 11,600 over eta, it is constant. What is eta? Now eta is actually, this is a PN junction forward characteristics graph for this linear portion, only for the linear portion. Eta is, the value of eta is 1 for silicon as well as for the germanium. Okay, for this linear portion, eta equals to 1 for germanium and silicon. For vertical rising portion, section. So Tk is the temperature Kelvin scale of room temperature 273, let room temperature is 25 Celsius. So K over Tk becomes now substituting the value here, 9.93 ID. So dVd over dId. Now I taken the reciprocal. Okay, 1 over 8.92, it is 0.026. Mean reciprocal of this. That becomes dVd over dId. The voltage over current, the variation, small d mean variation. When there is a variation, that resistance becomes AC resistance. So this is AC resistance, which is 26 millivolt over ID. Now if let ID equals to 25 milliampere, so how much it comes? 1.04 ohm. But I think if you calculate the same from the graph, the result was different. The reason is why we are getting the different results here. When the current, changes above 25 milliampere. Now here we are getting result 26 millivolts over 25 milli according to our derivation 1.04. Okay. So this is inappropriate. Now this, error it is because all the resistances level determined have been defined by the PN junction and do not include the resistance of the semiconductor material itself, which is called the body resistance, and the resistance introduced by the connection between the semiconductor material and the external metallic conductor, called the contact resistances. This discrepancy or error it is because we are not including contact resistance and the body resistance. So if we include the body resistance, the formula becomes, now this is 26 millivolt over ID, this one. I have added RB, that means body resistance. So then we are having the true formula, exact formula. Now RB, the value of RB, it is 0.1 ohm for higher power devices and 2 ohm now. If we consider, that formula was like 26 millivolt upon ID. This formula is valid only for the linear portion. Now what about if our point is close to the knee voltage? Okay, then the formula becomes RD equals to twice of 26 millivolt upon ID. Okay. Then the formula for the diode resistance is twice of 26 millivolt over ID. For example, if you are finding the resistance close to the 2 milliampere current, that becomes 2 into 26 millivolt upon 2 milliampere, and that becomes 2 into 13 ohm, that is 26 ohm. So this is the variation. If the point is close to the knee, then there's a factor of 2 in multiplication. Okay. So that's all about the difference between static and AC or the dynamic resistance. Thank you very much.